The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Okay, our first presenter is Sanjay Mehta. He's the CTO and Vice President of Engineering at Preload, Inc. The title of his presentation is Bond Strength of Diaphragm-Shotcrete Interface in Vertical Direction for AWWA D110 Type 3 tanks. Sanjay?
I want to thank you all for being here, and I want to thank Reza and ACI for arranging this session. As the title says, I'm going to talk about the bond strength of shotcrete diaphragm interface. Title of my presentation is Wire-Wound Precast Pre-Stressed Concrete Tanks with Continuous Steel Diaphragm. I'm going to talk in particular about bond strength of shotcrete diaphragm interface. The presentation outline is just brief description of design and construction of AWWA D110 Type 3 tanks. Now, just to mention, the corresponding standard is ACI 372. The reason why I mentioned D110 is some of the information that is in D110 is not there in ACI 372 as yet. So you can replace D110 with 372R whenever you want, corresponding ACI code. Then we'll get into the seismic load path at wall base joint, followed by pull-out test for shotcrete diaphragm interface. And that will lead us into discussion of development surface, which will be followed by full-scale pull-out test for shotcrete diaphragm base cable system to prove the concept of development surface, and then the conclusions. Now, what I'm going to present is particularly applicable for what I'm doing or what Preload does. It may not be applicable to other systems, so we have to understand that when I'm presenting the material. This is a typical cross-section of AWWA Type 3 tank. As you can see here, we have a ring footing cast monolithically with the floor. And one of the unique features of such tank is sliding base joint. So what we do is to ensure the water tightness at the base, we embed water stop in the footing during the construction. We also embed seismic base cables in high seismic zones to provide tangential resistance. And we have the wall, and this wall is made of precast sections, about 10 to 15 foot wide. And the way we do that is we put this diaphragm, it's a steel diaphragm, thin sheet steel diaphragm with ribs running in vertical direction. We put this in a horizontal position on the ground, and we pour concrete to the radius of curvature of the tank. And once the concrete hardens, we tilt up this panel and put it on the top of the bearing pad, which is resting on the footing. And that's how we complete the circle. And once the circle is complete, what you see from the outside is this diaphragm. Thereafter, we apply shotcrete and start wrapping the tank in a continuous fashion from bottom to top. That is, each and every point on the tank wall has a pre-stress counteracting liquid load, and then some more. So in other words, we are going to have some amount of residual pre-stress in the tank wall. And it is still diaphragm that provides excellent water tightness in this type of tank. And when you combine that steel diaphragm with the protection offered by alkaline-rich shotcrete, you get very good corrosion protection to prestressing wires. I'm going to show some construction slides just for sake of description. Typically, we get diaphragm in 3 foot wide section. We seam them together, and then we pour concrete, and we have a precast panel here. Now, there are some advantages to precast construction. I'll not get into details of that. But it should be intuitively clear that when you are tilting this panel up, we are putting a lot of flexural stresses on inside and outside faces of the wall. So, if you had a problem with the bond between diaphragm and concrete, there is going to be a separation during this operation. Many times, and especially for tall panels, the flexural stresses are controlled by this tilt-up operation. It is not controlled by service load condition. So if you had a problem with the bond between concrete and diaphragm, you are going to have a separation here, and when you do your water tightness test, it's going to be immediately evident that you have a problem there. So intuitively, one could say right away here that the bond in flexure is already tested to its maximum capacity, even before you put this wall in service. But then the question remains, what happens to bond between shotcrete and diaphragm? And this is the bond in flexure. What happens to the direct tension situation, which could occur in a high seismic zone? So that's the question we are going to look into today. This is the water stop encasement, just for information. And this is the prestressing operation, continuously from bottom to top, followed by shotcrete. And now let's look at the main problem that we are discussing here. Seismic load path at the wall base joint. So what we have is, we have earthquake load acting at the center of gravity of the system, which is going to generate the base shear here, which is transferred through tangential action. And that will result also into overturning moment. So you have a tension on one side and a compression diametrically opposite. This tension, if it is exceeding the dead weight of the wall and the roof, it's going to generate uplift forces here. And if you look at this diaphragm, it has ribs running in vertical direction. So in horizontal direction, you have mechanical interlock between concrete and diaphragm, shotcrete and diaphragm, which is pretty strong. But in vertical direction, the surface is plane. So the question is, how do you transfer this uplift load? So if you look at this slide, what we have is a seismic force here, and that is generating tension here. And if you look at close-up view, this tension, in case it overcomes the weight of the wall and the dome, will have to be transferred through this diaphragm into the shotcrete and into the base cable. So the concern is, and this has been raised by many people in high seismic zones, many consulting engineers are concerned about this behavior. So the question is, can plain vertical surface of diaphragm transfer seismic uplift force to the base cable through shotcrete? And when I looked at it, the only document that provides some guideline is D110 again. It provides a bond strength value of 2.5 square root of Fc prime, which is about 158 psi. Now, this value is probably more applicable in horizontal direction and where you have ribs providing mechanical interlock between shotcrete and diaphragm. The question is this value applicable in vertical direction? If it is not, then what is the appropriate value? Do you need to change your diaphragm fabrication process to increase this value? If not, what do you want to do here? And we do not have enough information at present in the public literature. There is some information about some research on bond, but not much. So, we decided to do our own test to answer these questions. And by this time, everybody must be thinking, what is the difference between bond strength of a reinforced bar encapsulated in concrete and the bond of diaphragm sheet? After all, there is 100 years of research done in bond behavior of rebars, and ACI 3408R is a state-of-the-art report. So what is the difference here? The difference is rebar is a line element, and it's a discrete system. That is, you space rebar at 6 inches, 12 inches, or whatever you have. It's not a continuum. The diaphragm is a thin metal surface, continuum surface, and if you use the specification ASTM A1008 and you fabricate according to that specification, the thickness is about 26 gauge, which is 0.017 inch. So even number 3 bar is 22 times thicker than this diaphragm. So if you try to apply the research that is done on the bond strength of rebars, it may not give you correct answers and guidelines. And this situation occurs only in type 3 tanks. So that is the reason why it is not studied very rigorously. It has been studied, but not very rigorously. So to do our own test, what we did was we constructed 2 specimens. Now keep in mind, we have built and designed more than 3,000 tanks, and some of them, more than 1,000 tanks using this concept. But I'm presenting the theoretical basis of how the whole thing works here. So what we did was we took a piece of diaphragm 18-inch wide versus 36-inch deep, and we applied shotcrete on either face at one of our job sites. And we constructed 2 specimens like this, and we shipped it to our testing facility, which was in Hauppauge at that time, and we decided to pull it out. Now, when one tries to pull this diaphragm sheet out of shotcrete, you want to ensure that it doesn't bend and break here. That is, you want to ensure that whatever failure mode that you are going to have is governed by the shotcrete diaphragm interface and not anywhere else. So in order to ensure that, what we did was we had to stiffen this projecting portion of the diaphragm, and we fabricated special steel reinforcing plate here, which we applied on the top and the bottom. We bolted it together and we gelled it. So this steel plate is stiffening entire diaphragm except at that interface where you have the load frame, and you'll see this load frame in the next slide, so that when you pull this shit out, the failure is going to be due to interface action here. And this is a test setup where what we have is we have a hydraulic jack here, which is connected to the load frame, and it's going to apply force in this direction. That is going to push the shotcrete surface here away from the diaphragm, because the diaphragm is being held in this system here, and that is going to pull the shotcrete away from the diaphragm. So what happens? We wanted to test the system to failure to get some idea, the basic idea. So what happens here is, this is the setup, and this is my co-presenter Don Cameron. He has been with the company for more than 40 years, and he has been involved with construction of some of the most complex tank. And I'm taking the photo here, so I'm not in the photo. All right. So we have a first specimen where diaphragm pulled out, and we observed about 3 inches of slip before load started decreasing. In the second test, we had diaphragm tension failure. That is, in the second test, the bond strength was much stronger than the tensile strength of the diaphragm. And why this happens? Because diaphragm is a very thin member there. So the bond strength in the second test was much more than the tensile strength of the diaphragm here. So if you look at it in terms of numbers, we had about 17,000 pounds corresponding to 26 psi for diaphragm slip, and in another one we had 21,000 corresponding to 32 psi diaphragm tension failure. So if you look here, right away you can see that the bond strength is in the same range as the tensile strength of the diaphragm, and there is no magic to it. You can do the numbers and you'll see that right away. So if you were to increase, for this type of diaphragm, if you were to increase the bond strength by doing anything that you want to do, you are not going to go too far. If at all you are going to go to 32.3 psi that you see. And keep in mind, in that case, the bond was much stronger. But let's say you want to do it. So you are not going to go any far, because the failure mode is simply going to shift from pull out to diaphragm tension, if that is already not the case. So what should be your design approach? How can you work with these values to ensure that you have a system that performs well in seismic event? The design approach that we have practiced is to mobilize sufficient surface area of shotcrete diaphragm interface such that failure mode is governed by yielding of base cable. That is, if you look at this system here, when you have a tension here, what you want to do is you want to have a loop like this that is going to mobilize the strength of shotcrete diaphragm interface in this area. And this area is what I call as development surface. So long as you mobilize sufficient strength of this shotcrete diaphragm interface here and ensure that the strength over this area is more than the yield of base cable, you are going to ensure that the failure mode is governed by yielding of base cable. And that is the fundamental philosophy of the course, that response reduction factor of arc equal to 3.25 in ACI 350.3 is governed based on the energy dissipation that is associated with ductile failure mode of the base cable, assuming that all other failure modes are precluded. And that is the assumption of the design. So how do we get that area? And that is the concept of development surface here. So you equate, you get the tensile strength of diaphragm, pretty simple, no magic there. And your bond strength, again, everybody would be familiar with these equations. And once you equate tensile strength to bond, you get the development length of the diaphragm. Even if you use the minimum value of bond, you will get diaphragm length of about 2.83 feet. So long as your loops are designed in such a way that your length that you are engaging on diaphragm is more than this, the failure is not going to be governed by bond. It is going to be in tension, right? And these are the values that you can get it from ASTM 1008 for the diaphragm. And I've used maximum value of diaphragm strength in terms of yield to ensure that I get the maximum value of development length. And the development surface simply then is L sub D multiplied by the width. And so the concept is to ensure the ductile failure mode, you want to engage the base cable in such a way, make sure I got that, yeah. You want to have a loop detail in such a way that the area enclosed by the loop has sufficient strength that will exceed the yield of the base cable. So that's a simple concept, and the way you do that is L sub D times W. Now, all this looks fine on paper, everything looks fantastic, and I have learned that you can prove virtually everything and anything with numbers. So the question is, does it work in reality? So what we did was, we decided to do a full-scale test here. We constructed a panel which is 5 foot wide, 6 foot tall, diaphragm ribs running in this direction, parallel to the base cable, and we decided to push one wall against the other. And we had 5 hydraulic jacks, 30-ton capacity, giving us total capacity of 150,000, about 300,000 pounds. What we did was, we held diaphragm, there are 2 sheets of diaphragm on either side of the concrete. We poured concrete inside of the diaphragm, and once it hardened, we put base cable on outside, and then we applied shotcrete. And that was our system. Now keep in mind, this system gives us a lower bound solution. Why? Because there are 3 very important things here. First, what is missing is pre-stress. Normal tank has a spirally wrapped pre-stress wires, and that provides tremendous clamping force in this direction, and that is missing. The second is confinement effect due to pre-stressing wire. What we have is, if you want to use analogy, when we have circular column wrapped with spirals, it provides excellent confinement to vertical rebar. And ductility of a spirally reinforced column is very well known. But that is missing here, which is going to be there in real case situation. The third thing is, we held diaphragm in vertical position and poured concrete. So liquid pressure of the concrete tends to push this diaphragm away. In real life situation, we are putting diaphragm in horizontal direction and we are pouring concrete. So anyway, I'm running out of time, so I'm going to show you this slide where we did this test setup, and I'm going to show the little video here, but I cannot see the mouse. Can you see the mouse here? Oh, okay, here it is. Okay. All right, so I'm going to show a little bit of video here, which is pointed towards the base cable here. And If you go further a little bit, yeah. So this load test was done to failure of the system, and we got about 6,500 psi reading here. That's what this gauge is showing eventually. In reality, it went up to 7,000 pounds. But if you compute the number, we got about 195,000 pounds of load, even without pre-stressing, clamping force, confinement, and even with the vertical pour. And that 195,000 pounds translate into 49,000 per leg of the cable, which is more than the yield of 0.6 inch diameter cable. So if you use 0.5 inch diameter cable, you are going to exceed the ultimate strength of that. So we are able to mobilize full bond strength. And the failure mode that you are going to see is somewhat like this, where you had a simple beam action, where the support is provided by the base cable, and the base cables tend to rotate as a simple beam towards the end, and that tends to push diaphragm out. And this kind of failure mode is going to be absent in real situation because you are going to have tremendous clamping and confinement due to pre-stress, plus you do not have the vertical pour effect. So this was crack that was indication of a separation of diaphragm from the pour wall at the 7,000 psi pressure at the failure. And as you can see, when diaphragm started yielding and pulling, it popped shotcrete out. And again, that is not going to be happening in real life situation. So with this system, lower bound solution, if you can mobilize full strength of the base cable, then for sure you know that in actual construction you are going to be able to do that. And the results are, I got about 42 psi of bond in vertical direction, even without confinement and pre-stressing effect. And actual construction is much more robust, adding to strength, system strength and ductility. And my conclusions are pull out of diaphragm in case of a seismic uplift can be avoided by proper detailing. You could increase the bond strength, but I don't know how far you can go with it. That is for our system again. You could have a different system that could have different implications. And proper detailing to mobilize the surface area of shotcrete is the best method to ensure full strength and ductility of system. With that, I end my presentation and will be happy to answer questions.
Maybe one or two short questions, if you haven't. Get over to the mic.
Whether the bond is brittle or ductile. And the other question is then, based on that finding, what power factor do you use to compute the phase load?
Okay, the idea is we are using R factor of 3.25 in our system design, and that is associated with ductile yielding of base cable. So we want to ensure that no other failure modes occur before yielding of base cable. So the idea of this system is to compute the loop design in such a way that your bond does not control. So the failure mode of bond is to be precluded from the design, and R of 3.25 is to be used, which is consistent with the yielding of base cable.
Thank you, Sanjay.
Thank you.